a fast proxy for curvature regularization in neural SDFs. Imagine you've just scanned a mechanical part. We fit an SDF with a neural network, but the surface still carries tiny twists and dimples, artifacts that never existed in the original CAD. Prior work removes those defects by minimizing full Gaussian curvature, yet that needs every Hessian entry, 7 backward passes per point, and huge memory. So our goal is simple: erase the warp, keep the clean geometry, and do it with first-order efficiency. The network's Hessian is a 3x3 matrix, but bending lives only in the 2D tangent plane. We first project that Hessian onto an orthonormal random tangent frame UV, which yields the 2x2 shape operator S. Of its 4 entries we calculate just one, the off-diagonal term S12. At every iteration we don't look only at the mesh points themselves. Instead, for each data point we draw one extra sample just off the surface, in a thin Gaussian shell. On that off-surface point we spin a random tangent frame, new angle theta every time, and evaluate only the single-value mixed second derivative in that frame. Because each S12 is a zero-mean random variable, averaging its square over the mini-batch is an unbiased Monte Carlo estimate of the expectation. Minimizing that average is therefore the maximum likelihood way to enforce zero warp, while the randomness keeps the estimate low variance and orientation free. Penalizing that single value S12 in each frame forces the principal curvatures to coincide, saddles and cylinders flatten, bumps round into spherical caps. Crucially, we now compute a single mixed second derivative instead of the full Hessian. Our network is trained with 4 terms. First, a Dirichlet term pulls every point cloud sample to 0, fixing the surface. Second, the non-manifold term penalizes unsigned distances in empty space, damping far-field oscillations. Third, the iconal term keeps the gradient length at 1 so the field remains a distance function. And finally, our curvature gap proxy drives the mixed shape operator entry to 0, removing local warp. On the ABC CAD benchmark, the new proxy matches the accuracy of Gaussian curvature regularization, same chamfer error, same normal consistency, but training runs about twice as fast and uses half the GPU memory. The code is a drop-in PyTorch module, so you can make your CAD reconstructions curvature-aware without paying the second-order tax. Thank you for watching.